ready to get started then? So, good morning, guys. My name's Sam. Welcome to Orchard Park Secondary School, home of FRC Team 2056. You can come ask me any questions if you have any at all. And I'd like to introduce our first speaker here, Michael J. Martin. And he's presenting the Internet of Things for the 2025 update, right?
Okay.
All set?
Good morning. Good morning. Thank you for having me, and good to see some friendly faces this morning. Do all of you know what the Internet of Things is or what it's about? Anybody? Yeah? Well versed? Know it very well? Okay. I've been doing it for about 20 years now, maybe 25. I don't even know. It's a long time. And I've done hundreds of projects. So all very crazy things, lots of robots, what we call robots, but you might see them as different things. And I went to high school here. I was actually a student in this room, but 56 years ago, a long time ago. So I went on, I was a terrible student. I was the worst probably student in the school, and had a terrible high school educational adventure. But I went on after high school, and I've been to many colleges, universities, and I have 8 degrees today. So I'm a lifelong learner. Since August 1st, I've done 8 courses on AI that I've done online on MOOCs, massive open online courses, if you know that, or micro learning as they call it. So I love learning new things and sharing knowledge. So I'm going to talk to you today about Internet of Things. And basically what we'll do, no, come on. Well, we'll do it the old-fashioned way. Yeah, the Internet of Things fails me. So we'll talk about 4 different things today. What is the Internet of Things in robotics? And how is it transforming? What are the innovations that are coming out? There's been a lot of changes this year. So the reason I picked this topic was because of all the innovations that's gone on in the last 12 months. One of the innovations is LoRa. LoRa is an acronym. It means long range radio. It's a radio communication system. So I'll touch on that. And then I will share with you a few things on how it may be used in FIRST Robotics. And I say maybe because I went and looked up all the rules. And there's lots of handcuffs on FIRST Robotics as to what you can do and what you can't do. But I think I've read enough of it, and I'm no expert by any imagination, but I think I've read enough of it to know that there's several things we can do that you're not doing today. So let's go through that a little bit. So first thing is, what is Internet of Things and how is it used? It's basically, we put a network together. So a network, typically it's a wireless network. It could be a wired network. We bring in automation, and that could use analytics. It could use AI. It could use just a Arduino card, like the way you operate today, where you have sensors and they trigger responses and make an actuator go. But it can be very, very enhanced, and there's a lot of new capabilities coming out with AI, and I'm sure you're all well versed in artificial intelligence already. So we'll just leave it at that, and we'll show you some real examples in a minute. We tend to use what we call the 3 I's, and the 3 I's are instrumented, interconnected, and intelligence. So these are the drivers that are driving IoT today. There's another version of IoT called IIoT, the Industrial Internet of Things, and that's normally what I work at. I'm not an IT guy, I'm an OT guy, meaning operational technology, not in information technology. So OT is the business, IT supports the business. Very different roles. So the three I's are really critical aspect to understand. So what are the instruments? We could almost add another one there, which would be actuators, and how do we take the information we get and then turn it into action? Okay. And if you have any questions, feel free to ask them at any time. What's one of the big changes that's happening is standards are evolving. And once you get standards, it has a double-edged sword. It slows down innovation. Any standards stop innovation. So we've had a lot of innovation to date, but now we're getting standards, which standards are good on the other side, is that you have interoperability and we can start to do things off the shelf. I always joke that the two dirtiest words I know in the English language are customization and modification. If you want to wreck your project, you want to make something go way over schedule or cost way more than you planned, then customize it or modify it. If you can use it off the shelf, that's the most economical and the best way to approach things. So we're moving into that stage of maturity of the technology now. Okay, so MQTT, has anyone heard of that? Anyone know what that is? You do. It's used in Facebook. It's used on many, many things, but I've used it a lot on IoT. For an example, I did a pipeline where a company bought, I'll say, they bought 7 companies total. All were pipeline companies, and they merged them all into one company. But all 7 companies use different SCADA systems. You know what SCADA is? You've heard that term? No? It's an acronym. We have lots of acronyms, and it means supervisory control and data acquisition, okay? And it's a command and control system. So we can control the pipelines and we can speed them up, slow them down, or sense if there's something wrong in the pipeline. That's a SCADA does that. But they had 7 different SCADA systems. They all spoke different languages. So none of them were compatible. So we ended up stripping off all the standards, all that they had, and we wrapped them in MQTT wrappers to make them harmonized. So we stripped it down to the data, used MQTT as a common wrapper, and then brought it into the single head end, and then made it all work on one system. It was a great way to do it at a low cost. So we love MQTT. Real world examples. I find that you can talk about technology, but unless you see it in action and how it's used, it's just theory. But I've got a lot of practical stuff behind me that I can share with you that you might find interesting. But the theory is that we can have autonomous systems that operate on their own, just like your drones do. And sorry, not your drones, your robots. And that they would be able to function and perform to a prescribed manner. Okay, so the most common thing you see is assembly line robotics, which is a big part of the future. I get in that a little bit in my career, but not much. It's just not something I've been doing, and it's pretty mature area. I like to do innovative things that haven't been done before. And then it's all about the sensors and the actuators and how do you take in data, make sense of the data, and then act on it. I'm a pilot, and in pilot training, they teach you that situational awareness drives better and faster decision making. Okay, that's sort of a mantra that my instructor taught me, and I live by that. Well, it fits perfectly well with Internet of Things because if we understand what the situation is, we can make better and faster decisions on what we want to do. And faster is becoming a very important thing, especially like autonomous cars, where you want them to go to process information very quickly. They have to be able to know that's a pedestrian, not to run them over. Okay, so speed of processing, we can't allow the data to go all the way to a cloud data center in the US somewhere and come back and tell us don't hit that person. Or is it a shadow of a person? Okay, if there's a shadow on the road, someone's standing at a bus stop, but the shadow is there early in the morning, does the car see the shadow as a person, or does it know it's a shadow? So it's got to be it's got to be done locally in the vehicle, which we're still getting there. Um, One of the big things is sharing data. How do we got the real time aspect, which I just mentioned, but we also have to share the data. And if you look at, I'll use cars again. We're going to have car to car, vehicle to vehicle, V2V communication. We're going to have even P to V, pedestrian to vehicle. We're going to have I to V, infrastructure to vehicle. I'll give you an example. The new Gordie Howe Bridge down in Windsor, as you approach it, it can start telling your car to slow down because there's a 3-4 kilometer backup to get on the bridge. Or it can automatically take the toll to cross the bridge for you. Or it can tell you, change lanes. You're in the truck lane, you need to be in the car lane. Stuff like this. So it's very, very important. And it's very adaptable in so much that it will adjust itself to the changing conditions. I just drove in from Toronto this morning, and the last 20 minutes I've been in a fog bank. Very thick fog as soon as I came from Burlington to here, and it was almost dangerous. Well, vehicles would not see the fog, or they would see the fog, but they wouldn't have the same problem that I had with my eyes. They would know there's stopped traffic up ahead. So it'd be much safer. It's all about coordination and communication. Here's one of the projects I did out in British Columbia, and it's autonomous mining. We did it as a pilot, and the dump trucks there, we used Caterpillar 793F dump trucks. They're 300,000 pounds empty. The tires are about 12 feet high. Each tire is $10,000. They have 6 of them on each dump. When they're loaded, they're 800,000 pounds. The Americans, so they still use pounds. I haven't got it in metric in my head. But 800,000 pounds is a whole lot of weight. It's like, 2,000 kilo or 20,000 kilos. Sorry, no, 2 million kilos. Excuse me. Lots of weight. Anything gets in its way, it'll die. Okay, nothing will survive. Another vehicle, a person, it's impossible. The maximum speed of those is 43 kilometers an hour when they go up the grade. And they run 24 hours a day. They don't need to stop for lunch. They don't need to stop for bathroom breaks, nothing. They just keep going. But we have to monitor the health of the vehicle. So we have so many sensors in these heavy equipment, it's unbelievable. For instance, each cylinder, there's a 12-cylinder engine, Caterpillar engine, and the Caterpillar engine in that thing is about as big as a minivan. It's gigantic. Each cylinder is like this big around, and they're individual cylinders. You can remove one cylinder at a time. In the language of the mechanics, they'll say it's throwing metal, meaning the piston's it's rubbing against the wall and it's scraping off metal. We have sensors in there that are magnets that in the oil, it picks the metal, goes and attaches to the magnet in the cylinder. So we can tell if it's throwing metal. So if we had to change one of the cylinders, we could know, oh, cylinder number 6 has got a problem. It's not aligned. We gotta change it out. But we might not have to change all 12 cylinders of the whole engine when the engine costs, $250,000. So there's a lot of things we do, and these heavy equipment, the dozers, the dumps, there's water trucks that just spray water to keep the dust down. The dust is actually, say, copper or whatever, if it's an open pit mine. You don't want your inventory blowing away in the wind. So all these vehicles are running all the time at full speed and processing the ore, whatever it is. This was a project for the Honda Allison plant south of Barrie, and they make cars, Honda cars. What we did there was we used the CPUs. There's about 19 CPUs, computers, processors in the car. Let's say one of the CPUs was for the distance for cruise control. But during the manufacturing process, we hijacked all the CPUs, we hooked them up, and we had them do other things for quality control. We had them test and judge if the quality is good enough. And is it working well? Are we building a good car? And then at the end of the assembly line, we reprogrammed them all to do whatever function they had to do. So the assembly line, they're building with robotics, but we're also doing quality control or quality assurance all through the manufacturing line process. Pretty interesting stuff. I deal with drones. I mentioned I'm a pilot, but I'm also a Transport Canada flight reviewer for drones, and I hold all the Transport Canada licenses, and I sit on committees. These are the type of drones I deal with. The top one on the right is a Heron, owned by the Canadian military. The bottom one is called a Predator. That wingspan is 86 feet wide. Okay, it wouldn't fit in this room. It's so big. And it'll go up for, I'll say, 32 hours endurance. Now we use, on the Heron, the one on the top, it's got a Rotax engine, which is the same engine that's in a snowmobile. Not quite the same, but similar. And it uses 2 carburetors. And we inject antifreeze into the carburetors to keep from the carb ice from forming. So it'll go up 20 hours and do surveillance, and they attach all sorts of things. The one at the bottom, you can see the control center for it, and they do it. They can operate them all the way around the world through satellite systems. So it's quite a different world than, DJI Mini 4 Pro or Mini 5 Pro now that just came out. So these are fun things to work on. Canada has a whole bunch of them. And they're patrolling, there's 18 of them patrolling the Canada-US border every day. You don't know that, but if you cross from New York State to Ontario in a boat, they'll see you. They're up there. None of them land in Canada. They're all operated by the US for Canada. But they all have, this picture doesn't show it, but they have Canadian flag on the side of them, so they are Canadian. Another project I did was for CN Rail, was to automate trains, love trains, big, powerful machines. The train tracks went from Chicago to New Orleans. It's like, I think 1,100 miles of track. So we had a PTC, positive train control. We could control the train on the whole journey from Chicago to New Orleans. So if there was crews working up ahead, we would know that, and we would slow the train down because there's workers around the bend. If the gates didn't come down at a crossing, we would know that because the gates have IoT sensors on them and are talking through radio systems. We put 1,800 towers along that track right away, and then communicated all the data all along. Now, they don't need to know when they're in Illinois, they don't need to know what's going on in the South. They just need to know in their vicinity. So we can throttle the trains, how fast they go. We can read the train, the health of the train. Is it working properly? Is everything cool? And then we can control it on its journey and go make it go faster, make it go slower, make it deal with a car that's stopped on the tracks. We would know because we had cameras at crossings and we could transmit the video feed back to the engineer in the train. Very fun project. Another one that started out with Bombardier. Bombardier made an airplane, a jet airplane, which was later sold to Airbus and is now the Airbus 220. Air Canada flies a lot of them. You may have been on one. What's interesting is that in each engine, these Pratt & Whitney engines, there's 5,000 sensors in each engine. In each wing, there's 5,000 more sensors. We're measuring the flex, the width, the lift, the twist, all the parameters of the wing in nanoseconds to see what's going on. Then they're micro throttling the engines. Go faster, go slower, go faster, speed up, so we can get optimum fuel performance out of the engine. That's 20,000 sensors outside of the fuselage. There's more inside the plane. But the pilot can't manage 20,000 sensors. So the plane is managing itself. It's doing all that command and control. And it's feeding a dashboard to the pilot so he can see what's going on. So he'll set the speed that he wants to achieve, and then the plane will make that speed, but at the most fuel efficient capability. This Airbus 220 competes against the 737 from Boeing. It's 20% more fuel efficient than the Boeing 737. And in aviation, 20% less fuel is a huge, huge competitive advantage. So a lot of fun stuff there too. Now, I'll say to you, what do you see here? Anybody? What do you see? What is it? It's a bridge, of course. But what I see is something very different. We call it the song of the bridge. To me, it's like a guitar. It's an instrument. So we listen to the guy wires. They make songs, they make tunes. When the bridge is new, the guy wires have a certain harmonic music to them, and we can listen to that. Now, if a crack happens in the concrete in the bridge, just like if there's a crack in the fet on the guitar, it would go out of tune. So by listening to the song of the bridge, we can tell that there's something wrong. Likewise, we can listen to all the guy wires and we can triangulate where the problem is. On top of that, we put sensors right in the concrete. So we can use the song of the bridge from the guy wires, also the concrete itself, to help us understand. And there's all sorts of dynamics like wind temperature, wind speed, wind direction, water, temperature, speed, ice, all kinds of different things. Like if you have an accident at the toll bridge, then all of a sudden, all the vehicles are going to back up. If it's on a weekend, the vehicles are going to be cars, but on a weekday, like a Tuesday, they might be transport trucks. Each transport truck could be 80,000 pounds, a lot of weight. So what you have then is you have to take into account the structural loading, what's the weight of the bridge, what's the environment around the bridge, and what's the load on the bridge at the time. What else could be a load on the bridge? Ice, snow. All kinds of things can change the song of the bridge. So we had to account for all of that in the design. And it works really cool. It's quite a fun thing. So now, what are the innovations? What's going on? What's new? The biggest thing we're getting now is low latency. How fast, or time of flight, we call it. How long does it take for the datagrams or the packets to go to and back? We call it round trip. What's the round trip time? When I started, we were in 500 milliseconds, which was half a minute. When we got it better, we got down to 200 milliseconds per round trip. Now we're down to about 6 and 8 milliseconds. That's 6 1,000ths of a second. So that speed allows us to act more quickly and more efficiently. And we've also, when we started, we were running at 3 kilobits a second. Okay, now we're running at megabytes per second. So we're getting a whole lot more data, whole lot more information therefore we have to process that information, but we can't send it to the cloud. We have to process it locally. So latency is a really big issue, especially when you have multiple things that have to interact with each other, whether it's cars on the road or robots on an assembly line, they all have to interact. Edge computing is another term. Edge computing doesn't necessarily mean AI, but it could. But edge computing is bring in data from sensors, process it in some way, and then act on it with actuators. That's a very simplistic term. Now, how you process it, it could be through analytics or all different. It could be just a FPGA like you use in the robots. It could be a field programmable gate array. It doesn't need to be high-tech million-dollar AI, but it could be AI if we want to do that. But the more delay, AI takes time to process information, and again, we work in milliseconds, then that could hurt us. So sometimes we don't use AI because it's too slow in a millisecond universe, okay? But other times we do use AI a lot, a lot, a lot. What we're using AI for is machine learning. The deep neural networks, deep learning, is very hard to put in a small processor. It's doable, it's happening now. Like some of the new cameras we see coming out have the new Sony that's just about to be announced next week has a huge AI processor in it with deep learning. It's one of the first I'm seeing. But previous to that, all the AI we've seen in devices has been machine learning, a more simplistic, trained, manually trained, single function type of processor. It was do one job, do it really well. But with deep learning, it can learn, it can adapt, it can change, and it can grow bigger. So if we can make 20 devices, and each one of them may function very different from each other a year from now, because they've learned in different environments, learned in different settings. Just like you guys are all students in school, maybe you're all in, say grade 12, but then you go off to university and you go off to all these different programs, you change. In the beginning, when you're in high school, you're kind of all the same. But then when you get out into university and some of you go into biology, some to robotics, some to engineering, whatever, then you're all changing your path forward. And that's the same way that AI is going, is how, if it's able to learn, they all start sort of at the same point and then they diverge over their experience of time. So it's kind of interesting to see that. One of the fun things, and this came out about 15 years ago, we started to have, I'll say, virtual reality and augmented reality. I remember Google or Apple, I can't remember, they brought out glasses that you could wear on your head and you can see, and then they terminated the whole project, killed it right away. Well, it's all coming back again. After a decade of very little, all of a sudden we're getting a whole lot coming. And it's exciting. I loved it back then, and I was really disappointed to see it go away. But it was, I remember 15 years ago, if you were a pilot and you were flying, you could see the checklist of all the things you had to do, say for landing, are the flaps down, is the gear down, all these things could show up in your glasses. Not very great, actually, a long time ago, but now I can see it be a lot more. A friend of mine works at a high-tech company in the US, and he is a jogger, and he had some technology that blew me away. He goes for a 10K run before work, okay? He's a very fit guy, and he uses an iPhone with music into his earbuds, but he has sensors he puts on himself on his chest so that the iPhone hears his heart rate. It selects the music for the pace of, like, say, warm up to the run, at the run, and cool down after the run. And then it also gives him maps and tells him when he's in a different city, because we all travel for work. He doesn't know where is safe or not safe. It tells him turn left, and he's hearing it in the music, turn right at the next corner, because it's going to keep him safe. Or maybe he wants to avoid big hills, or maybe he'll tell it what he wants in the way of his run today. I need an easy run. But it selects the music, and the beat and time of the music is timed to his heart rate, so that he can have the music, you get the rhythm, and then he can get the rate of running to correspond. And when he's cooling down, it changes the rhythm of the music as well for the cool down. It's very cool. So someone's working on as a development thing. And we're seeing now mixed reality. I don't know if you've heard that term, but we're mixing together. You can have a phone and hold it up and look at a street, and it will tell you all the businesses in the buildings, for instance. So you're seeing real. It's showing you maybe business cards to say, I'm looking for an optometrist. Then it'll tell me there's one here in this building, that sort of thing. Now, LoRa, LoRa's maturing. It's been around 15 years. It started out that you can buy lots of sensors. Anybody use LoRa at all? Has anyone tried it? No? It started out as a 900 megahertz radio system, and it was designed for Internet of Things. It goes very far. I've seen it go 20 kilometers, okay? But it only ran at 3 or 6 kilobits a second. It was very slow in the early days. Now it's running at megabits, and it's still going even farther. Now it can do 15, 20 kilometers easily, robustly, you know? So it's pretty neat. And it's a standard, and you can buy sensors from China that are pennies, fraction of pennies for sensors. There's thousands of devices you can buy that work on the LoRa network. It's a lot of fun if you like to build things and hook things up. My friend Peter owns a vineyard on the bench. They call it the bench down here near St. Catharines. And we instrumented the whole vineyard. We put sensors in for temperature of the soil, for acidity of the soil, and for moisture, and then brought it all through LoRa network and Peter wrote a C++ program to map the whole vineyard so he could see. Why? Because he did an organic vineyard, no chemicals, no nothing. It's all organic. So he needed to know where he had to put water down and where he had to put manure down because it's very labor intensive. So he didn't want to do the whole field because he had like 16 acres of Pinotage grapes. So he just wanted to put it where it was needed. So he had a whole program done for that, which is very cool. So as I mentioned, the magic of LoRa is long range. It goes really far. It uses a University of Hawaii modulation technique called slotted aloha. In Hawaiian, aloha means hello and goodbye. So it handshakes back and forth. And slotted, visualize a train going by, and each car has so much capacity. Whether you put data in the car or not, you always have to put something in. So we call it bit stuffing. We just put in ones and just fill it up. So the cars go by, but we know the beat of the cars. We know how fast they're going to go, and we know that it's going to go long range. And we load it up with data. So it uses that Hawaiian modulation as a foundation, but its main magic, it's very low power. So it can go to sleep. It doesn't need to be powered up all the time. Wi-Fi is very power hungry that you guys use, and it just sucks in electricity. So it's not great on batteries comparatively. LoRa would go weeks where Wi-Fi might not even make a day because of the power drain. So LoRa is ideal for robotics, and if you're going to get into robotics on a higher level, it's going to be everywhere you go. And I'll tell you that it can go into very hostile environments. Like a room like this, look at all the machinery in here. All this machinery could be making RFI, radio frequency interference, or it could be making EMI, electromagnetic interference. LoRa can punch through all that. Where other systems like Wi-Fi, well, anybody who's got a microwave oven at home, it operates in the same band as Wi-Fi. You turn on the microwave oven, you can knock the Wi-Fi out of service. Okay, I don't know if that's happened to anybody, but it's very common. So LoRa is very robust, and it's great for remote monitoring and for coordination of systems. The other aspect is very secure, and it's very stable. So it will work all the time in harsh environments. We use it in the oil field for the pump jacks that are pumping the oil out of the ground. There are big distances between those, and they're all connected with LoRa in that 900 megahertz band. But LoRa now, one of the innovations is they'll work down at 220, at 450 megahertz, 220 megahertz, and it'll work in Wi-Fi band at 2.5 gigahertz. All sorts of different frequencies now LoRa can work. It used to just be 900, 902 to 928 megahertz. It's also extremely secure. It's all encrypted, so no one's going to hack into it. The Semtech this week announced 2 new chips that they're for LoRa. Semtech invented LoRa, and they're a company, and they've now pushed it into the standards community. It's open; anybody can access it now. And so the new chips that they're making will increase the speeds to 2.4 megabits per second, which is when we started with 3 kilobits. That's quite a big difference. So, how does it benefit FIRST Robotics? Where could you use it? I had to speculate a little bit. So, I did some research. I learned about some of your rules and what's around, but I saw it as data collection, performance insights, and then strategy refinements um, for the competitions. Okay, these are three highlights that I'll put forward. Now, you have a lot of restrictions as to what you can do and what you can't do. So, what frequencies can you use? What radio systems can you use? They're restricted. You have to use the processor that they give you, that they direct you to, which is Robo. I call it Robo Real, but I think is that how you guys would pronounce Real? Yeah. So you use that processor, but that processor is good, but it's been locked in its development for a while. So you can do other things. I found that you can use a Raspberry Pi in your robots, but as a secondary function to the Robo Reel. Am I right on that? So I was thinking now you could use it. I read that some teams, and maybe you guys are too, are using it for vision systems, camera systems. Is that right? That's not what I read. So, but what else could I do with it? Could I instrument the robot? Could I pull telemetry out of the robot? Could I see the health of the robot just like we do with the mining? Why not? What else can I do? And and all of a sudden, I've got all this data coming in, and just like the bridge I talked about, we can have mixed data. And mixed data would be real-time data coming out of the robot, real time. Okay? We know what's going on right now. But it can be historical. Maybe data from the last 5 years of speed of the robot, telemetry of the robot, performance of the robot. Can we take that historical data in and use that with the real time as patterns, trends, anomalies? Can it help us to learn and to perform? If it goes into an AI in the Raspberry Pi, then can it optimize performance in the competition? And then you have environmental data. Now, unlike the bridge where we're looking at temperature and wind and all that stuff, you might be looking at what do you call it? The course? I'd call it the course, the field. Field, yeah. Thank you. So you might be looking at it differently as to where the obstructions are, where the other teams are, where the competition is. You might even be analyzing their performance. I know we can see it. I've been to the Paramount event. I've been to MAC and watched the events. So I see how it works. But what else can I get out of it? What else can I use? And especially when you're teaming with another team and collaborating, how can I use that to my advantage? So it's not only competing against the other teams, but also collaborating with your partner teams. So the types of data that you get and how you use it is very, very important. As I mentioned, I looked at the rules. I tried to follow it all. What I learned was the rules come out every year for each year, and they don't come out till around the first week of January. So all I could look at is the 2025 rules, which are not going to be the same rules, I would assume, as 2026, but probably maybe 80%, 90% the same and some differences, right? So normally that's how I see it. One of my friends, Richard, is one of the judges for the Ontario Regional. So I called him up and asked him some things about it, and I got some insights. I'm not sure which competitions he judges, but I know he's been involved. I have a few friends that have been involved in FIRST Robotics. We're all ex-IBMers, so just so you know where I come from. So you have to stay within the rules of the competition. No argument, no doubt. Otherwise, you'll be judged and disqualified. So it's really important to not violate the rules. And we'd have to look at that. And then the wireless rules. I looked at the wireless, what they do. There's times when you have to be autonomous, and there's times when you have command and control. There's times they have very strict rules on the radio frequencies that you can use and the power levels and everything. So My assumption is you're using Wi-Fi and you're using unlicensed or license exempt spectrum. You're not licensing anything, but you can't interfere with the other team's Wi-Fi. You can't blow them off the air. With Wi-Fi, we have very strict power level settings and strict modulation. There's a whole bunch of stuff there that is controlled and confined. And but not LoRa, but the IoT will work over Wi-Fi. So we can do that now this year that we might not have done in other years. And Bluetooth too, you're using Bluetooth, but there's different Bluetooth functionalities too, different versions of Bluetooth with different range capabilities that might be very viable here too. But I saw it more monitoring and diagnostics. You would want to take a crawl, walk, run approach to this as to how you could use it without violating the rules. But the thinking I had was I'd want to start learning, listening to the robot, understanding what it's doing, and then why is it doing it, and then start to analyze that data to optimize it offline, so to speak. And then learn from that, and then get into more real-time stuff as you progress. I'm a big fan of Raspberry Pis. I have about 10 or 12 of them. And I took 8 of them and made my own blockchain out of them. So I've played around with it a bit. I took the free courses at University of Michigan and Python. I've taken 3 of them now. And they're pretty good. So I've tried programming. I've done different things, played around with it. And I like them. They're pretty cool things. I like Arduino as well. We used a lot of Arduino app at that vineyard that I mentioned. So that, when I looked at FIRST Robotics, they say you don't need Arduino, just use Raspberry Pi. But when I looked at the RoboRio card, it's got it looks like a hybrid between a Raspberry Pi and an Arduino card to me. So just looking at it, I don't know what's under the covers. But you even have a Robot Pi for Python, so you already have coding that we can use. So I think it would be pretty easy to do this. And how do we take in data from the sensors? How do we make decisions? And then how do we act on it? That would be very interesting. I'm at the end here now. So in summary, it's data sharing, improved communications, and strategic actions. How do I take the information I have and make a decision out of it? Now, whether you're doing that for FIRST Robotics or whether you're doing it for your work life later in life, these principles are the same. So you can have the slide deck if you want this, by the way, at the end. But just to conclude, I see IoT as transforming the robots completely, and we're in the beginning. It was just turn left, turn right. It was so rudimentary. Nowadays, it's so much farther than that. It's intuitive. It's autonomous. It's very, very adaptable, and I like that. It greatly enhances a robot's capability, whether a robot's an airplane, a train, or a dump truck, or a FIRST Robotics robot. It's all the same to me. So you can really add, and it's all about now collaboration, and in your case, competition, right? As FIRST Robotics, and then the last final point is pushing intelligence to the edge. This is a theme where we used to have. If you look around at many systems today, we would have a cloud center, and the cloud would hold all the knowledge. So we'd have to have a really robust network to transport the data to and from the cloud. That adds latency. Now we're pushing all the intelligence into the robot itself. It will collaborate with the cloud, and it will tell the cloud everything's good. Instead of sending it the data so the cloud decides if everything's good, it just confirms everything's good. So very simple communication. But the cloud can come back. We'll have deep learning in the cloud. We'll have machine learning in the robot, okay? And they'll collaborate together. But then it could also collaborate with other robots, whether it's assembly lines or trains on tracks, that sort of thing. because you can't run a train without knowing there's another train coming at you on the same track. So and that train might be 200 kilometers away. So you need to know situational awareness, what's going on. So I don't know. Any questions? Is that all putting you all to sleep? Am I boring you to death? Makes sense? No? Disagree with anything? It changes so fast that, especially the AI part, the stuff we were doing in AI 1 year ago is not what we're doing today. I've been doing AI for 33 years. You guys think it's new. It's not. It's old. My first AI project was on the space shuttle. Space shuttle's not even operating anymore. 33 years ago, we put a camera on the space shuttle, a 4K camera, but it was only black and white those days. We didn't have color in 4K. And we were doing a pattern and color and shape analysis. And we wanted to forecast if the citrus crop in Florida was going to be a big harvest this year or a bad harvest. So we flew over it with the space shuttle and took pictures of the state of Florida and tried to analyze. The whole thing was a complete failure. Yes.
Are you mentor of this team, 2056?
Sorry, say again?
Are you a mentor of this team, 2056?
No, I'll work with anybody. I favor 2056 because I was raised here in Stony Creek, but I've helped a lot of teams in Canada, and some of my friends are involved in different ways in FIRST Robotics because they came to IBM and asked us to help. Yeah, FIRST Robotics and IBM's been part of FIRST Robotics for a long time. I don't know if they still are. I've been out of IBM for 6, 7 years. So
How do you use IoT device on robots? Like a real example.
how do I what?
How do you use IoT devices on robots in addition to Raspberry camera?
Well, I'll give you an example. In Ancaster, you know where Ancaster is, the other side of Hamilton? It was secret at the time because IBM didn't want to be associated with marijuana. But when marijuana came, they're building greenhouses in Ancaster to grow marijuana. Okay, so I got put on the project, and the greenhouses were going to be 1.1 million square feet. 11 greenhouses, 100,000 square feet each. They were all pressurized, positive PSI. They're climate control, light control. We use cameras to look for insects in the air. If there's bugs flying around, we wanted to know, right? The 4K cameras, new cameras at that time, could see the bugs. But we also used the cameras, we calibrated them. I have 31 years of broadcasting behind me, broadcast engineering. So I know how to calibrate a camera for color, right? So we calibrated the cameras to look at the chlorophyll in the plants. We're trying to get the plant life from 22 weeks to 16 weeks. When I left the project, we were down to 18 weeks. So they're making real progress. But the environment was critical. So we had to control the light. So the roofs were all glass, but they had blankets. And when 3 blankets were in, there was 0 light coming in from outside. They removed the first blanket, 20% gets through, 80% is blocked. Second blanket, 50-50. Third blanket, it's 80% gets through, 20 doesn't. And then full open, 100% of the light. You can't shock a plant with too much light. You can't give it light 24 hours a day. It needs to sleep, it needs to rest. So we used computers, we used AI to control the humidity, the temperature. The temperature in the growing greenhouses was different than the temperature and the humidity in the drying greenhouses. The growing was like 21 degrees Celsius and 60% humidity. The drying was 20% humidity, 85 Fahrenheit, which is probably around 30 degrees Celsius. So little 28 maybe. So if you see what I'm getting at here, there's many ways to use it depending, and we even looked at the pressure in the room. so that we could control the environment and keep bugs out. The first time I went into a greenhouse, they gave me a hazmat suit, like a fireman would wear, like with a hood and everything. I never had one of these before. And the PhD from University of Guelph, who was our host, I said, well, this is really good. I said, I have asthma. This will help protect me from anything in the greenhouse that might trigger my asthma, you know? And he said, oh, no, it's not for you. It's to protect the plants. He says to me, you're a fat man, Mr. Martin. Fat men have mold. Ouch. And he said, we don't want anything on me to come in contact with the plants. I thought it was for me. It was the opposite. So I don't know. There's all kinds of things that you can use it. It's infinite, really. And we've done, even you go to Tim Hortons, right? So Tim Hortons, if they have a bakery on site, which most of them do, they make their own product. They roll in the drums of dough in 60-gallon drums. And then they they know the yield out of a 60-gallon drum, how many donuts it will make. They tie that into the cash register to see if the revenues match the yield of product. It's unbelievable, right? And they control the temperature of the refrigerators at every Tim Hortons to make sure that they're all perfect and that there's no bacteria or anything that's going to harm the public, right? It's good use of IoT. All kinds of stuff. You wouldn't believe some of the things we've done that we're not doing. At one chain store, we were reading the MAC IDs of the phones when you walked in the door. Okay? So we didn't know your name, but we knew your MAC ID because that's not encrypted. We didn't know any of your data on your phone, but we knew the MAC ID. So we could see, oh, this MAC ID showed up at this store 3 times this week, right? And they would triangulate you in the store. So if I'm walking around the store and I see a big display of snow tires and I'm standing there looking at the snow tires, and if I'm a member of their points club, they now know me because my membership allows them to access me. All of a sudden, my phone pings, and I open it up, and they send me a message, 10% off tires today. I'm standing right in front of tires. Well, they know that. That's why they sent me trying to get me to buy the tires. Say I stand there another 10 minutes looking at the tires, haven't bought, haven't moved. Just looking, and maybe I go look from Goodyear, I go look at Michelin. Oh, they're expensive. Bing, now 15% off Michelin. They know where you are in the store, right? They're tracking you. And if you knew some of the things that were being done, you would be horrified because of privacy legislation, right? So there's many ways to use it, many ways to abuse it. Nowadays, buildings are becoming green buildings, right? And we can control the elevators, access control, escalators, lighting, control fire systems, fire suppression systems. Everything is integrated, and it's called BIS, Building Information System. And you go into a modern building today, you'd be shocked at how much we can control. We can even tell if the fire exit signs lights are burned out, so we know to do repair. Sorry, say again?
Use case of IoT devices in the FRC robots.
I'm not getting that. Sorry.
Any application of IoT devices, sensors
What-
in the FRC robots.
What kind of devices else? I'm sorry. IoT. Oh, IoT devices in there. Yeah, there's a really great company in Spain that makes sensors, and I'll remember the name in a minute. But the biggest one I use is Bosch, the automotive company out of Germany. They make hundreds of different sensors, and they have. So, what sensors do you need? Motion detection, impact sensing. Like, why does a robot break down in competition? You know, it all starts with the question. It's not not the technology. What's the problem? What is it I want to solve? So it's the question that drives the technology selection. One time, McCain French fries, you know McCain, right? A big company. They have barns. They harvest potatoes in New Brunswick. Millions of potatoes in a barn waiting for a transport truck to pick them up. If mold gets in there, then the mold can go right through the whole millions of potatoes and they're all garbage. So we created a nose, a digital nose, a sensor that smelled mold. We put them in the barn all over so we could triangulate where the mold was. You know how they did it before? The farmer used his own nose. He'd go in, smell around, and now we're using. So it's not what technology can you put in a robot. It's what problem do you have? Tell me your problem. I want to understand the problem. Then we'll find the technology that can fix it. When we made the digital nose, I had 23 sensors. The second version, I had 15. The last one, I had 7 because I kept refining it down to 7 sensors is all I needed. I could get everything I want. But understanding the problem and getting the right answer to the problem is what's really important. Any other questions? No? Was that good, bad? Okay. Okay. Thank you very much. Appreciate your time.
Thank you.